Okay, good evening, everybody.
Good evening.
Tonight's presentation will be Observation of Nano-Hertz Gravitational Waves by Dr. Paul Bloom, Associate Professor of Physics at North Central College. Gravitational waves were first observed in 2017 by the LIGO experimental collaboration. Required by general relativity, these waves resulting from the mergers of compact stellar mass objects took almost 100 years for physicists to identify and resulted in an almost immediate Nobel Prize in Physics. Now physicists have identified another source of gravitational waves with frequencies in the nanohertz range. The discovery required the long-term observation of millisecond period pulsars for more than a decade, and has opened the door to a new range of phenomena. In this talk, Dr. Bloom will discuss the basics of gravitational waves, the use of pulsar timing arrays to measure them, what was actually observed, and what it all might mean. Dr. Bloom is an experimental high-energy physicist and has taught at North Central College since 2006. He has a BA in physics from Reed College and a PhD in physics from UC Davis. Paul is currently a collaborator on the Muon G2 experiment at Fermilab, trying to poke a hole in the standard model. Beyond high-energy physics, he has interest in astrophysics, climate science, and climate mitigation efforts. Please welcome Dr. Paul Bloom.
I want to thank you all for having me here tonight. And if there are any astrophysicists in the room, I apologize in advance. I am not an astrophysicist, but I think it's really cool, so I like to play at it in my spare time. You know, it's a funny thing. I get to teach a class on stellar structure and evolution every few years. And when I ask my students, you know, do you think it's interesting that we know how stars work? And they're like, yeah. I'm like, has anybody ever been to a star? Measured anything directly on it? No. Huh. How do you think that is? Science. So, but my talk tonight is about nanohertz gravitational waves. Interesting stuff. It begs many questions. First of all, what's a gravitational wave? And by the way, we must distinguish between gravitational waves, which are a general relativistic phenomenon, and gravity waves, which have to do with densities and fluids and interesting things like that. So we're going to talk about what gravitational waves are. We're going to talk about how one goes about observing gravitational waves, and how do we actually detect them in the nanohertz frequency. Nanohertz. That's a really low frequency. It's a billionth of a cycle per second. That's changing. Is that even a wave? How can something change so slowly? So we'll talk about that. And at some point we'll actually get to what was measured, which is the interesting part. And then what does this tell us about the universe? If at any point something needs clarification, it is literally my job to explain things. So interrupt at will. So the first thing we have to know about is general relativity. The theory of general relativity is Einstein's theory of gravity. And it is currently our best descriptor of what gravity is and how it works. The entire theory flows from a simple but really incredibly subtle assertion that the laws of physics must be the same in all frames of reference. And notice that includes both inertial and non-inertial. So things that could be accelerating. Special relativity restricts itself to inertial frames of reference. General relativity is general because it says no. Physics has to be the same in all frames of reference. Einstein followed this he said, look, we're going to take this assertion at face value. Why do we think the world works that way? Well, he found it odd. Perhaps it's from an aesthetic point of view, or from whatever he felt was right about how what the nature of physical law has to be. But he thought it odd that somehow physics should depend on how you observe it. And so whether you're in a coordinate system that is moving at constant velocity or one that's moving in changing velocity, why should that matter? Well, it turns out that that idea is already immediately runs afoul of Newton's first law. Newton's first law says, no, 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 right? Objects in motion tend to remain in motion unless acted by a force. In other words, it says, unless you have forces acting on an object, it should just move around at constant velocity. It shouldn't change its speed, it shouldn't change its direction. And Einstein says, no. So Newton would say that's nonsense. But it turns out, if you are willing to take that assertion at face value, and again, you follow it where it goes, you apply rigorous logic, you learn something. And this was the genius of Einstein again and again, not just in the development of relativity, but also in his understanding of the photoelectric effect, and even a lot of the groundbreaking work that he did in the development of quantum physics, which later on he didn't like where that went, so he had some problems with it. But nonetheless, Einstein did foundational work in all of these areas. So what general relativity tells us, ultimately, is that space and time are not separate entities. They are different aspects of a deeper space-time. And that relationship gets introduced in the study of special relativity, but x and t don't become just two coordinates, right? In Newton's physics, position is where you are, it's where all the action is. I tell my students it's kind of like a football field, right? You want to know what's going on, that's position. But up on the scoreboard, there's time. And everybody agrees on time, and time is just this universal thing. And in special relativity, Einstein makes the first step towards saying, you know what? Time matters too. And somehow they're involved with each other. And again, that comes from the assertion that the laws of physics must be the same to all inertial observers. So general relativity puts them on a truly equal footing. Space and time, or x and t, are just coordinates. And it turns out that in certain circumstances, they get mixed up. Inside the event horizon of a black hole, the direction of going radially inward gets so turned around that that is the same as going forward in time. That's literally, from the perspective of general relativity, why you can't escape from a black hole once you pass through the event horizon. It's not that the pull of gravity is too strong, but rather, going forward in time is the same as going radially inward. There's simply no choice. Space-time becomes the fabric of the universe. It's the stage upon which all the things play out. It's very, I guess, Shakespearean. The force of gravity, according to Einstein, is an illusion. It's an illusion created by our Newtonian brains, right? And our brains are Newtonian because that's what we grow up observing, right? We don't live close to incredibly high-density objects that might bend space-time appreciably. We don't spend any time going, at a good clip of the speed of light, or any time being as small as atoms or molecules. So these are things that, quantum physics and relativity are all anathema to us, because that doesn't make any sense. That's clearly not how the world works, despite the fact that all the measurements that we make, all the experiments that we perform, tell us, it is, sorry, it's just that you happen to be very big and very slow and don't happen to live near a black hole. So our Newtonian brains see objects accelerating when they're near large masses. And of course, Newton told us that forces cause things to accelerate. So if something is accelerating, there must be a force, and that's gravity. But what's really happening is that matter and energy, and of course those two things are interchangeable, E equals mc squared, matter and energy cause space-time to curve. The fabric of space and time is not flat, it's not a nice uniform grid, it's distorted. And those distortions cause things trying to move in straight lines. Well, it changes the definition of what a straight line is. And that curvature then gives rise to the illusion of what we call gravity. All of general relativity can be summarized, in fact, with the idea that matter and energy cause space-time to curve, and the curvature of space-time causes matter and energy to accelerate. And that was coined by John Archibald Wheeler, one of probably the top 5 general relativists of all time. And so you come up with this equation. It's a rather innocuous looking equation, except that these things are actually tensors, so this is shorthand for, 4x4. So this is 16 nonlinear differential equations, oh my. But this thing G tells you something about the curvature of space-time, and this thing T tells you about the matter and energy in space-time. And together, right, they're related to each other. So they talk to each other. And notice Newton's constant of gravity shows up in here, the speed of light shows up in here. Interesting stuff. I can tell you from my own personal experience in graduate school, general relativity is hard. It's hard because the ideas are hard, but also the math is hard because the math that you're doing is calculus on an arbitrarily curved manifold. Okay, those are words. It's hard. So, more things that general relativity tells us. It gives us a fundamental way of understanding what gravity actually is. Right? Newton couldn't do that. Newton simply said, oh, masses exert forces on each other. Einstein tells you what is gravity. It's the ability of mass to curve space, to cause space-time to curve. And it's the ability of other masses to sniff that curvature out and behave accordingly. The mechanism by which and this is ultimately the mechanism by which what we call gravity reaches out across space-time, right? That for Newton, he had no idea why it was that the sun could reach out and affect the motion of the Earth. Einstein tells us, right? The curvature of space-time affects the motion of Earth through space-time, and because that motion is through curved space-time, Earth appears to go around in what is very nearly a perfect circle around the sun. What's our orbital eccentricity these days? 0.03 or something like that. It's very small. General relativity also fixes the causality problem in Newton's gravity. Newton had no way since Newton doesn't know the mechanism for how this mass can affect this mass, Newton also says, well, if I were to delete that mass, this other mass would instantly start going in a regular old straight line. That means that that influence must have been propagating at infinite speed, which is a problem, which is a huge problem. It breaks causality. There has to be some kind of speed limit. And so, in general relativity, those distortions, those ripples in space-time, can only propagate at a finite speed. And that speed turns out to be the speed of light. So it fixes gravity. It gives you an actual mechanism, and it makes it well behaved in terms of cause and effect. We like cause and effect. There's no cause and effect, you go home, right? Your time as a scientist is pointless. General relativity gives us what's called the principle of equivalence. It's the reason why the inertial mass of an object, what's the inertial mass? Well, if you write down Newton's second law, F equals ma, that m tells you if I want to get a certain acceleration out of a given mass, I have to apply a certain amount of force. It's the proportionality between the force you apply and the acceleration that you get. That m is called the inertial mass. And yet, in Newton's law of gravity, there's a different m. And yet we use the same symbol for it. And in fact, if you go out and measure the inertial mass of an object, and then you go out and measure the gravitational mass of the object, it's exactly the same number. No matter how precisely you measure it, they're the same. And Newton knew this, and physicists for hundreds of years knew this, but why? This is what the principle of equivalence does. It says, no, they have to be the same because that's the property of an object that appears in that stress energy tensor thing, and it also is the thing that appears in the the space-time curvature. So the bottom line is, it solves this mystery that probably you've never even heard of. But why are those two versions of mass the same? Well, Einstein has an answer. It's a nice story, but like any story in physics, it's only as good as the tests that you place on it. So, how do we know that general relativity is right? Any theory must produce testable results, and then we must go out and test them. There are lots of famous GR tests that have been done. Many of the most famous ones stem from the idea that gravity can influence light. We know from quantum physics that light is really massless photons. And if something doesn't have mass, how on earth can gravity affect it? According to Newton, not possible. But in Einstein's theory of gravity, because we're talking about the curvature of space-time, it alters the trajectories of all objects, including photons. Light. So gravity can bend and accelerate light. Newton simply can't do that. This was first observed back in 1921, maybe, just a couple of years after this was predicted by Arthur Eddington and others. They went and looked at a solar eclipse, and they found, hey, we know where a certain star is, and of course, it's pretty close to the sun right now, so we can't go looking at it during the day, but you can observe its position during a solar eclipse. And they found that when you did this, the star was in the wrong place. Why? Because as that light traveled from the star toward us, it had to pass fairly close to the sun. And the sun's gravity bent that light, meaning that instead of you thinking, oh, the light is coming from over here, the light is bent. So now it bent around the sun, and it looks like it's coming from over there. Stellar aberration of starlight, or gravitational, rather, aberration of starlight. So this was the first experimental verification of general relativity. Yes, sir.
You mentioned the photons being massless. I have a question with that, because if something affects something, it must have a mass, albeit so small we can't detect it yet.
No. What do you mean? What do you mean affects something? Well, because what we mean by a massless particle is a massless object is something that follows a specific trajectory through space-time. Clearly, Newton's second law doesn't make any sense. I mean, think about all the problems that you have if m is equal to 0. But it turns out in relativity, when you look at what happens to an object that has 0 mass, yeah, it gives you a crazy number. It gives you a nonsense result, unless that particle happens to be moving at the speed of light. So there's a loophole in relativity.
Oh, it's a blink then.
So the only way you can have a massless particle is if it travels at the speed of light, and the reverse is true. Only things that travel at the speed of light can be massless. It's a tricky one, and it's a detail that's buried pretty deep in special relativity. But that means that photons can interact, and again, their primary job is to interact with things with electric charge. But a photon is also sensitive to gravity because as a massless object, it has to traverse a path through space-time called a null geodesic. And in any case, that path is defined by the local curvature of space-time, which is created by mass. But that's a tough idea. Other predictions. Well, because gravity can bend light, can accelerate light, it gives rise to the phenomenon of gravitational lensing. Now, That wasn't observed until many years later, but we use it all the time now. In fact, it's one of the primary ways that we weigh distant galaxies, right? If we have a distant galaxy and we would like to know how much mass does that thing actually have, we look at its ability to lens light sources behind it. And the amount of lensing determines the mass, and that tells us, amongst other things, that galaxies are quite often heavier than we think they ought to be based on the amount of luminous matter in them. But that is a very different lecture. Gravitational redshift, the idea that even if forgetting a black hole, but if you look at light coming from a very large galaxy, from that's been emitted, for instance, light that moves past a neutron star, the wavelengths are shifted. And the wavelengths shift, they're stretched out because of gravity. In a sense, that's what a black hole really is. It's something that when you get close enough, any light being emitted from that object becomes infinitely gravitationally redshifted, and therefore no light can escape. So all of these things have been observed. Gravitational self-energy, what does that mean? Well, strong gravitational fields store appreciable amounts of energy in the field in the same way as electric and magnetic fields do. The field itself contains energy. And since mass and energy are equivalent, that energy, it causes additional curvature of local space-time. That has effects. And one of them is that it makes the gravity of the sun, especially when you're close to the sun and the curvature is more extreme, a little bit stronger than you think it ought to be. When people observed the orbit of Mercury, they saw very early on that the orbital axis shifted as a function of time. The perihelion position shifted as Mercury not only orbits the sun, but the axis of the ellipse also shifts over time. And when you go to calculate that with Newton's gravity, it gets it wrong by not a small amount. Well, in general relativity, it gets that answer right. We like that when theories get the right answer. There are more tests. There's a long list of other predictions that general relativity makes and that Newton's gravity does not. For instance, gravitational time dilation. Again, things like this are observed near neutron stars, near central black holes, but this is a phenomenon that's been seen. There's something called gravito-electromagnetic frame dragging, which I can't explain it to you because I really don't understand it myself, but it's a thing, and apparently its effects have been observed. And of course, gravitational waves. No such thing in Newtonian mechanics, but in the theory of general relativity, there are waves, literally undulations in the fabric of space-time that propagate through space-time. And of course, this we care about. Now, there are other places where general relativity makes some predictions on the cosmological scale, but here there seem to be some issues. If we look at galactic rotation curves, if we look at large-scale lensing observations, if we look at galaxy cluster velocity distributions, if we look at the large-scale structure of the universe and the acceleration of the Hubble expansion, those things in our current model of cosmology require the existence of dark matter and dark energy. In fact, those are our primary, that's why we talk about those things. But another way to explain it would be if our understanding of gravity was incomplete in some way, especially at large distances or for very small accelerations. And that's the idea behind modified Newtonian dynamics. That is the topic for another very interesting conversation. But when somebody comes along and tells you, oh, there must be dark energy, there must be dark matter, that makes the assumption that general relativity is completely correct. And maybe it isn't. Maybe we just don't have enough experience observing the universe in those particular extreme ranges. Okay, so we talked about gravitational waves, and so this is one of the major predictions of general relativity, that accelerating masses will cause ripples in space-time that will propagate outward from those masses. And that's the essence of a gravitational wave. The ripples propagate, as do all changes in space-time, at the speed of light. Like any other wave, they can come in any frequency, and hence any wavelength. Right? Frequency, as always, the frequency times the wavelength has to be equal to the wave speed, which in this case is the speed of light. Since these are ripples in the fabric of space-time, as they propagate, they cause space-time to literally stretch and compress. It literally changes the distance between objects as these things move through. Nothing stops or absorbs gravitational waves. Right? We know if you want to do infrared astronomy from the ground, nope. Why? Because our pesky atmosphere is really good at absorbing infrared radiation. Right? Ditto for ultraviolet, X-rays, all that good stuff. We have to go to space and get above the atmosphere. No problem with gravitational waves. They go through everything. Nothing stops them. Nothing absorbs them because they are ripples in the fabric, they're in the stage, right, of space-time. So this is, whatever's riding around on it can't absorb it. That makes them really hard to detect. But it also makes them incredibly useful because you can use gravitational waves to probe some of the most extreme conditions in the universe, right? You want to look into the heart of a galaxy where maybe there's some, supermassive black hole, something is going on there. The center of a galaxy is often clouded by dust and by gas and is opaque to us in many wavelengths of electromagnetic radiation. Not so to gravitational waves. If we get good enough at observing them, there is astronomy to be done with gravitational waves. And a kind of astronomy that you can't do with anything else. Yes?
Does anything, or can anything modify gravitation? Let's just say a black hole. If a wave goes through a black hole, is it as if the black hole's not even there? Or does it somehow change the wave?
Well, remember, a black hole is static, right? So it's sitting there, and it's clearly a very large distortion in the curvature of space-time. It's conceivable that something like that might scatter, might redirect a gravitational wave. I'm not sure. That's a great question. I really don't know the answer to that. Yes?
Is space-time, does it follow superposition?
Waves are waves. It absolutely does. So if you have two gravitational waves and they come up and you're at a location where their peaks are lined up, you're going to get a bigger gravitational wave.
So might there be a place in space where all these gravitational waves have come together to form a giant thing that looks like that there's a mass there that actually is just the sum of all these waves up there?
Conceivable. There could be a place where where it's completely flattened out space-time. Yes. Superposition always works for waves. Yes.
Can you use gravitational waves to actually find something that you can't see optically?
No idea. You're looking for something that you can't see optically. I mean, certainly if it's massive enough to deflect a gravitational wave, it's more likely that we would use gravitational waves to look for the kinds of things that create them. And we can talk a little more about what that means. Yes?
How synonymous is gravitational waves to quantum foam?
Different beasts. So the quantum foam, I think of as, so these are quantum fluctuations in the background, or rather in the fields that represent all the particles that we know about. And so the quantum foam is the idea that particles can pop into existence and then vanish back into the quantum vacuum, essentially. So the classical vacuum is empty. The quantum vacuum is full of all kinds of stuff. And the closer you look, the more stuff there is because of the uncertainty principle. So not the same. And in fact, one really important thing, and that is that this description of gravitation is classical. It does not incorporate quantum principles. Moreover, it actually doesn't play well with quantum principles because the quantum foam at the level of understanding what is space-time, that would break general relativity. We know general relativity breaks down at some point for exactly that reason. It's one of the greatest mystery in all of science. Yes?
Forgive a woo-woo question, but if space-time can be stretched and compressed, does that open the door, theoretically, for a warp drive?
I think, again, you have to, how do we create such a thing? I mean, from what I understand, that's exactly what warp drive is. Compress the space-time in front of you, stretch it out behind you, and so within that bubble, you don't exceed the speed of light, but you literally make the distance in front of you shorter. Realistically, the energies involved in something like that are astronomical. But possible? Sure, why not? And do you really want to live in a world where there's no Star Trek? I don't know. So, I'll go ahead and say, absolutely possible. Other questions? I mean, all this is a little woo-woo, right? This is way out there. So, but we'll get there. So, gravitational waves can be created by anything that generates what is formally called a non-zero second time derivative of the quadrupole moment of the stress energy tensor. Oh my God, we should not say things like that. For our purposes, what we mean by that is that anything that causes the mass energy distribution of an isolated object to vary with time. Here are some examples, right? Two objects orbiting each other. There is clearly a time-dependent motion, right? The distribution of those two masses changes with time. That generates gravitational waves. In fact, right now, at this very moment, as the Earth orbits the Sun, the Earth is emitting gravitational waves because it is accelerating. About 200 watts worth. Where does that energy go? Well, it's radiated off into space. Where did it come from? It came from the rotational motion of the Earth around the Sun. That means we're very slowly losing energy. If you have any sense of the kinetic energy of the Earth in its orbit, you know that 200 watts is nothing to worry about. We're not going anywhere anytime soon. But if we're talking about two neutron stars orbiting each other, or a couple of stellar mass black holes, that starts to matter. And those things radiate enormous amounts of energy, and they're visible all the way across the universe. That's the kind of thing that LIGO has actually observed. If you have an asymmetric object, so say a neutron star with a mountain on it, or a supernova that was somehow asymmetric, that will generate gravitational waves. And then there's weird stuff from the early universe, having to do with cosmic inflation, having to do with topological defects at the end of inflation, where the universe fundamentally changed itself. Those, in principle, can also produce gravitational waves. Again, weird, but possible. The frequency of the gravitational wave is determined by the production mechanism. So, two neutron stars in-spiraling, orbiting faster and faster, those are going to generate fairly high frequency gravitational waves. 100 hertz, kilohertz, right? These are actually the things that LIGO has observed. So here's a list of things. So here's my perfunctory animation of two in-spiraling objects creating ripples in space-time, or at least in a two-dimensional fabric of some sort. And you can see that there are, keep forgetting I had this pointy thing. So here's the wave period. Some of them are really short, milliseconds, seconds, hours, years, age of the universe, right, for the wave period. How long does it take for that wave to repeat itself? Or in terms of frequency, 100 hertz, 1 hertz, millihertz, nanohertz, ouch, really, really short. And you can see the different kinds of things that make them. So a rotating neutron star, a rotating asymmetric neutron star, an asymmetric supernova. These are going to produce fairly high frequency gravitational waves. Compact binaries. So these are the things that LIGO has been happily observing now. Mergers between stellar mass black holes and neutron stars, between two black holes, between two neutron stars. Those produce a range up to, you know, a few hundred hertz, maybe even a kilohertz, and down to a millihertz. When a supermassive black hole captures a compact object, so in the center of some galaxy, a star wanders too close to a black hole and gets captured and sucked into an accretion disk, that can produce gravitational waves, and those have somewhat longer frequencies. So remember, a lower number here is a much longer period, a much slower wave, not in terms of speed, but in terms of how quickly it repeats itself. And by the way, that means the wavelengths here are getting longer and longer and longer. Yes?
So with all these cumulative objects adding their waves together or whatever, would it almost be safe to say that each galaxy would have its own unique frequency for the overall wave propagation throughout the galaxy?
If we could measure all of the gravitational waves, all of that activity, we would find out that, well, it's not that it has a unique frequency, but rather it has a unique spectrum, right? A certain amount of this and a certain amount of that.
Yeah.
You know, maybe there's a galaxy that has lots of stellar mass black hole mergers going on. So they would have a stronger short frequency component.
So you do an FFT on those signals and quantify?
But in a magical world where I could detect all this stuff, the actual detection doesn't work anywhere near that well yet. But yeah, you could, right? And you would say, oh, anything that, you know, the component that shows up with these at these higher frequencies, those are these, and maybe compacts and compact binaries and so on, and you have a sense of what's out there. Notice binary supermassive black holes, much lower frequencies, much longer periods. These stretch out from the millihertz out into the nanohertz. So these are really slow things. These are actually, this is what would be produced if you had not stellar mass black holes, things that had, you know, 2 or 10 or 50 times the mass of the sun, but black holes that maybe are 1 million solar masses or 1 billion solar masses, right? These are the things that live in the centers of galaxies. And then all the stuff from the early universe, right? It could be anything from the primordial cosmic gravitational wave background that gets stretched up by cosmic inflation to all these weird other things that are out there. People get really creative when they talk about the very early universe, and there are no constraints on them in terms of anything that's been observed. This is the problem with theorists, right? They need data to constrain them, or they're incredibly creative, but also they're incredibly creative. Okay. So, how do we go about detecting these things, right? I've been avoiding that so far. Again, this is difficult. They interact very weakly with matter, and what we have to do is we have to rely on the effect that they have on space-time as they pass through. Can we observe that effect? Specifically, can we use the compression and stretching of space-time to observe the effect on light waves, because that's something we are really good at measuring, that travel through the space-time that's being distorted. And so interferometers, things like LIGO or LISA, which is a planned space-based interferometer, do exactly that. And I'll show you how. High-precision clocks based on the arrival time of light pulses from highly regular astronomical objects like pulsars can also do this trick. The basic idea is that a gravitational wave that passes along the path that is going to be taken by that light will cause the path to become a little shorter or a little longer as it passes through, and that will cause the timing to change, right, from our vantage point. If you have an interferometer, you get a shift in an interference pattern. Or if you have something like a pulsar timing array, you get a shift in the timing measurement of the arrival of these pulses. And the approach that you use connects the size of the detector to the wavelength of the waves that you can measure. And if they're badly mismatched, you're not going to measure anything. And I'll show you what that means. So here is LIGO. LIGO is an interferometer. What it does is it sends laser light on two separate paths. So there's a laser, there's a beam splitter, and actually the light bounces back and forth many times, and there's some other goodies happening here, so that even though these arms are 4 kilometers long, the effective length of this thing is actually substantially longer. The light is eventually brought back together and projected, and you see an interference pattern. And the exact pattern is irrelevant. What matters is if something comes along and distorts the length of either one of these sides, the pattern shifts because you have stretched or compressed the path that the light travels. And that shift, it can be decoded to figure out, A, that a gravitational wave has passed, and also you can figure out the strength of that wave. What was its amplitude? By how much did it stretch or compress the path length? And if you have several of these things, and you have exact timing, and they're oriented in different directions, you can even do some triangulation. Oh, which direction did that gravitational wave come from? That's the beginning of doing astronomy with them.
It's two LIGO and just one Virgo right now, or are there more?
2 LIGO, 1 Virgo, and there are several others being planned. So by the time, 10 years from now, they're going to be, half a dozen of these things all over the planet. And again, the sensitivity of this apparatus is astonishing. Ultimately, what they're measuring, just to give you a sense of how much space-time is stretched or compressed, typically, one of these arms, its length changes by the diameter of a proton. Interferometers are magical. They're just really good. LIGO can detect frequencies anywhere between about 200 hertz and 10 kilohertz. And by the way, assuming that wave is traveling at the speed of light, that corresponds to wavelengths between about 1,500 and 30 kilometers, right? So, all right, 30 kilometers is not so different than 4 kilometers, especially since there's a lot of back and forth. But much shorter than that, these wavelengths are going to be very hard to measure because it's going to be too small. Much longer than that, and again, the wavelength will change, the wave will change so slowly with time that you won't be able to detect what's going on here. So there's a tie-in between the size of the gravity waves that you can measure, their wavelength, and the physical size of the detector. So notice, this thing is measuring somewhere between 200 hertz and maybe 10 kilohertz. Where does that live? It all lives out here. So LIGO can see compact binaries. It can see rotating neutron stars and supernova, but it's not going to see any of this stuff. It can't. Now, LIGO is really interesting, and it's so interesting that someone wants to build a longer version of it with an arm length of, instead of 4 kilometers, of 5 million kilometers. Now, obviously, you cannot build this on the surface of the Earth, so this has to go out and live in space. And if they build, this thing is called LISA. People are serious about building this thing. LISA will be able to measure frequencies from a hertz down to even a fraction of a millihertz. And that means gravitational waves with wavelengths of 300,000 kilometers up to 3 billion kilometers. So we're talking really long wavelengths, really low frequencies. So now we're out here. And maybe LISA will clearly measure compact binaries, but it should be able to catch compact objects being captured by supermassive black holes. Maybe it will see some binary supermassive black hole mergers, and now it's starting to sample a bigger chunk of these more interesting things that people are speculating about. So when you start putting this all together, and you find out that, okay, a terrestrial interferometer can get these guys, and space-based interferometers can get these guys, but there's a limit, right? You can only make this thing so big, right? And by the way, one more piece of stuff that they want to put out at L2, right? So for its L2 Lagrange point, there's already a lot of stuff out there, and they want to put more. I mean, it's a great place to put something if you'd like it to stay put out in space, but also it's going to get crowded. Pulsar timing arrays can be sensitive from microhertz out to nanohertz. Really, really, really low frequencies, and therefore very, very long wavelengths. And notice now you're picking up, right, more of these supermassive black hole mergers, right? This is at least a decade away, if not more. But this is happening right now. And by the way, radio dish, right? This is done with radio telescopes. In principle, you can measure even the lowest low frequency gravitational waves from the cosmic gravitational wave background, and you measure it by polarization of the cosmic microwave background. In fact, a few years ago, there's a measurement from a collaboration called BICEP, where they thought they had actually seen this. The problem was it turned out that they didn't know how to subtract the signature of dust from their measurements, and so it went away. But this was very exciting because this actually happened before LIGO. Win some, you lose some. Okay, so what is a pulsar timing array? Now that we're 45 minutes in here. Okay, so to answer that, I got to tell you what's a pulsar and what's getting time. And how are these things sensitive to gravitational waves? And how are they sensitive to very low frequency gravitational waves? How does it even work? So hopefully we're in more familiar territory now. When a massive star, usually about 8 times solar mass, undergoes at the end of its evolution, it undergoes a core collapse, usually type 2 supernova. And the result is a compact remnant. Either a neutron star, as long as the remnant is not greater than about 2 point something solar masses, or you get a black hole if it's bigger than that. So neutron stars are all sitting in this sort of 1.4 to 2.3 solar mass range. And a neutron star is exactly that. It's an object formed entirely of neutrons. The neutrons form when the protons and the electrons in a collapsing star literally get pushed into each other, and they undergo inverse beta decay, and now you no longer have a proton and an electron, you have a neutron. And so essentially all the matter in the stellar remnant is converted to neutrons. The density of a neutron star is essentially the same as the density of an atomic nucleus. It is staggering. And what's left, this remnant, remember, comes from a star that maybe was 8 or 10 solar masses. So a lot of the mass of the object, or at least a big chunk of the mass of the object, is still there. But also things like its angular momentum and its magnetic field. Except that now, instead of an object which is, the size of a star, it's now 10 kilometers across. But it still has a big chunk of the angular momentum of the original star, which means it spins really fast. It also has almost all of the original magnetic field, which means that the magnetic field near the surface of a neutron star can range from 10 to the 4 to 10 to the 11 Tesla, or more if you're talking about something really exotic like a magnetar. For reference, the Earth's magnetic field is about 1/2 times 10 to the -4 Tesla, half a Gauss. So we're talking about something that is 10 to the power 8, right? At least, and more like 10 to the power, 15 more times the Earth's magnetic field. These are magnetic fields of staggering strength. And they spin really quickly, some of them rotating as often as every few milliseconds. So this thing is spinning like crazy. It's got an enormous magnetic field. It's incredibly compact. And that magnetic field is so powerful that it can actually generate a beam of high-energy electromagnetic radiation along the field axis. So this is happening because the thing is both spinning and it has a magnetic field, and typically the axis of rotation and the magnetic field don't quite coincide. And as a result, you get this thing that just beams out light. And when I say light, I mean radio waves, and infrared, and visible, and in many cases, ultraviolet, and X-rays, and even gamma rays, depending on the situation. So now when they do that, they're beaming away energy. And what that does, that energy is coming from the rotation of the star, of the neutron star. It actually causes it to slow down very slowly, but noticeably. Some neutron stars have debris fields, right? They just come from a core collapse supernova. There's all kinds of gas and stuff around. These things accrete matter. They create accretion disks, and that matter in spirals, and when it does, you're converting gravitational potential energy into heat, right, in the accretion disk, and that thing gets so hot that, again, it will beam electromagnetic radiation, and again, that comes out along the axis of the magnetic field. But in this case, the neutron stars don't spin down because the energy is not coming from the rotation of the star, but rather from the gravitational potential energy that the infalling matter liberates. And so when the magnetic field and the axis of rotation do not coincide, you get this beam of light, except that it's off axis. And if that beam happens to intersect you, the thing blinks on and off. And pulsars can be, again, visible throughout the electromagnetic spectrum. Here's an example. This is the Crab pulsar. It's a X-ray plus visual composite, and you can see the accretion disk, and you can even see a hint that this is beaming stuff away. Here's the idea. Here's the neutron star, itty-bitty guy. Its magnetic field is here, and the magnetic field axis is here, and yet the rotation axis is offset. The result is something like this. Whenever that thing passes you, if you're up here, you see nothing. But if you happen to be over here, when that beam comes by, then what you see is blink. That's the essence of a pulsar. All pulsars are neutron stars. Not all neutron stars are pulsars for us because you have to be in the right place. So you have a neutron star, and it has an accretion disk, and that infalling gas fuels the pulsar. And essentially it turns all that gravitational potential energy into electromagnetic radiation. But it turns out that most neutron stars don't actually start spinning quite that fast. What happens is that infalling matter was also part of that original star, in all likelihood, and it itself carries some angular momentum, and as it falls in, it actually speeds up the neutron star. Best evidence today is that millisecond pulsars, there really are such things. They spin with rotational periods of just a few milliseconds. They're actually really old pulsars that have grown up in binary systems with a lower mass star. So a higher mass star lives its life, blows up, it leaves behind a neutron star. When its lower mass partner eventually becomes a red giant, the neutron star can steal gas, and it actually will speed up. And so you get these really fast neutrons, these really fast, quickly rotating neutron stars. Notice that means that pulsar frequencies can actually change in both directions. They can speed up and they can slow down. But in both cases, this happens really slowly. And actually, the timing associated with, especially with these faster pulsars, is so good that it's comparable to the best terrestrial atomic clocks. That's how good the precision on these timing events is.
So when you say really slowly, 10 years, 100 years, a billion years?
Millions of years. Millions of years. So over the span of 20 years or 100 years, no, you're not. They are perfectly stable, right? Again, over cosmological lifetimes, yeah, they spin up, they slow down. That's going to happen. We're not around for that long, so as far as we're concerned, they are perfectly stable. It turns out you find lots of these things in globular clusters. The main reason is that those are such compact, busy places, right? Lots of stars nearby, lots more stuff to feed on. And again, when we're talking about pulsar timing, what we mean is the timing between those pulses. That's what we're measuring. And again, not perfectly stable. Pulsars do spin up and down, but it happens really slowly. So it turns out that millisecond pulsars, again, stable over hundreds of years, certainly over periods of time for as long as we've been observing them. And again, if you average over decades, the precision and the stability of these millisecond pulsars is essentially comparable to terrestrial atomic clocks, which is mind-blowing. And so measuring pulsar timing is just, it boils down to getting a radio telescope. I mean, you can observe them in X-rays sometimes, but radio telescopes are easier. They're on the ground. We have lots of them. And you just watch the thing blink. If you want to observe them in X-rays or gamma rays, you have to put up a satellite. That's a pain. They're hard to service. Now, with one pulsar, you can, well, if you can time one, you can time many of them. Why? Well, because when you have lots of pulsars, they're distributed all over space, in all directions, at all distances. That's just a really cool idea, so why not? What pulsar timing arrays do is it allows us for precision measurements of what are called stochastic phenomena. Random gravitational waves, things where we're not looking to identify a source at this point. We just want to know if they're even out there. And if we're right, there is a sea of gravitational waves. They slosh all over the place. There are so many different sources for these things. They are just everywhere. Can we see them? And that is the first application, right? That's for pulsar timing arrays. In principle, there are others that require precision non-terrestrial timing. Here's the idea. Here's our friend the Earth. And here are a bunch of different pulsars. And they all have their different axes, but hopefully the beams cross the Earth. And the point is that we know the distance to these, well, even if we don't know the distance to these things, we know the timing, but that timing is affected by the curvature of space-time. And in particular, if the curvature of space-time along that path changes, a pulse might show up a little earlier. A pulse might show up a little later. How much earlier? How much later? Not very much. It turns out you have to watch these things for a long time. Why? So again, the idea is that pulsar timing tells us about gravitational waves. And the basic idea is that the passage of a gravitational wave will compress or stretch space-time. And so if the wave propagates, that wave propagates along your line of sight between you and the pulsar, then the arrival time of the pulses might speed up or slow down. If the wave propagates at right angles, it turns out there's not much of an effect at all. So that already tells you something. And it turns out that if you look at arrays of pulsars, then you can look at the correlations between the fluctuations in timing and the angular position of different pulsars relative to one another. that gets complicated. The more pulsars you have, the better, and the longer you look, the better, because if you're looking for a nanohertz gravitational wave, that means it has a period of about 30 years and a wavelength of 300 light years. A wave with a wavelength of 300 light years. That blows my mind.
Do you care how far away they are?
The pulsar?
Yes.
No.
Yeah.
As long as I can accurately measure it. So in 1983, a couple of gentlemen by the name of Hellings and Downs analyzed what would happen to a pulsar timing array with using millisecond pulsars under the influence of gravitational waves. And again, you just have to think their waves are coming and going, they're going in all different directions, lots of waves. What they found is that even if the waves were completely random, there would still be a distinctive signature, which they call a quadrupolar spatial correlation between arrival times of pulses emitted by different millisecond pulsar pairings that depend only on the pairing's angular separation from the Earth. That's complicated. It just means that depending on where this one is and where this one is, there's a prediction for, hey, this guy just showed me some pulses that arrived a little more closely together, and this one did something else. What is the correlation between those two things? And it turns out this is a much more clever thing to do. It's a much more sensitive thing to do than looking at just one particular pulsar and waiting for something to change. So the idea is, right, here are 3 different pulsars. They're all sending their pulses with different frequencies, whatever, from where they are toward the Earth. And here comes this gravitational wave, and it is going to compress or stretch space-time in some way. And notice it's going to affect this guy first, and then maybe this guy. And also because it's traveling this way, maybe it's going to affect this one the most, but a little bit later. So they calculate this curve. It's called the Hellings-Down curve, and it's a plot between the correlation between any 2 pulsars and the angle of their separation. And it gives you this funky shape. And I have not done this calculation. I do not know where this comes from. I have no intuition for what this means, but I know that that's the theoretical prediction. Well, so we went out and did, or rather, scientists did the measurement. There are actually multiple international collaborations that are looking at millisecond pulsar timing arrays. Some of those have been going on for more than 15 years now. In particular, in June, the NanoGrav collaboration released their data from an array of 68 pulsars that they've been looking at for the last 15 years. And since then, 3 other collaborations have corroborated their evidence, all their observations, although with less data. But now more people are getting into the game because all you need is a radio telescope and to know where some pulsars are, or at least millisecond pulsars. And their data confirm the presence of stochastic gravitational waves in the nanohertz range at a confidence level of 3 standard deviations. What that means, and I'll show you the plot in a minute, is that there's a small but non-zero chance that this observation could be an accident. It could be noise. 5 sigma is usually the standard, and that's a sort of a 1 in a million chance. Again, listen, this is in the good old days, and by that I mean when I was a grad student and I went to a talk, an astrophysics talk, and the errors were and the uncertainties were in the exponents of things, not in the 1% precision. Right? This is a different game. We live in an age of precision astrophysics now, so this is plenty good. Yes.
So you said all you need is a radio telescope. Can an amateur astronomer do this? Or are you talking like you need like $1 million?
So I know that the Chinese got into the game late because they now have the world's largest single radio receiver, and they have been doing this. I don't know if could you get a 3-meter dish from an old C-band satellite TV antenna and make a radio telescope? I don't know.
You have to be able to point it.
You have to. I mean, assuming you could point it.
I'm not sure if this question makes sense, but let's say you detect a gravitational wave. how can you determine if it's just a single event or it's a cumulative event?
This is cumulative, and because spoiling. Here's the data. This curve is what you predict if you have a large collection of randomly traveling waves, right? And you can see that. So again, here's the Hellings-Downs curve. Here is what you would see if there were no gravitational waves, no correlation between timing, right? There's no correlation between angular separation and changes in the timing of these pulses. That's not what they saw. They saw this very clear trend that seems to map along with this thing. The error bars are big, right? That's why this is a 3 sigma, experiment, and not a 5 sigma experiment, right? That there's still, you could imagine with a little bit of squinting that no, these are all just, it's an unlucky day, and in fact, this is just flat. Nanograv says that by 2025, they will have collected enough additional data, plus pulling in all the other observations that people have made. And by the way, they're not all observing the same pulsars. There is some overlap, but they pick different pulsars. So there's a lot of information to be had. But they predict by 2025 that they could beat this uncertainty down to where it's 5 sigma. Good question?
That one diagram, it reminds me of a cosmic strain gauge.
You're not wrong. There's definitely something going on. Look, anytime there is a specific correlation between things, right? That's telling you something. Again, I do not understand the physics of why it takes on that particular shape. But what I do know is that the people who performed this analysis understood this, and they were able to come up with this correlation curve, and it looks different than what you would expect if there were no gravitational waves. It's not the most convincing data in the world, but more is coming. And if you shrink those error bars, you might have a much better sense that it's following that curve. And it is. You don't have to look at this too hard. That it starts up, it goes down, it comes back up. Given the size of the uncertainties, that's pretty impressive. So these things are out there. What does it mean? So what? Well, again, the most likely source of these nanohertz gravitational waves is the merger of supermassive black holes. We know this has to happen. And we know this has to happen because it's a cannibalistic universe, right? Little galaxies get eaten to make even bigger galaxies. Big galaxies eat little galaxies. We know that the Milky Way has several satellite galaxies that it has recently eaten or is in the process of eating, right? That goes on all the time. And yet galaxies all have black holes in their centers, right? Every single one. It's exceptionally unusual to find one that doesn't. And so if galaxies merge, their supermassive central black holes must merge. Maybe. Well, that's certainly the easiest interpretation of this data. The problem is, what's the mechanism by which this happens? When people try to do the calculation, they run into a problem. It's called the last parsec problem. Getting supermassive black holes to actually merge turns out to be trickier than anybody anticipated. There's probably some missing information. So maybe, though, if this background is coming from supermassive black hole mergers, then clearly nature has found a way that we don't understand yet. Something really interesting is going on there. Measuring the amplitude, right? Not just are those waves there, but how big are those waves? Because that tells you something about the masses of the objects involved. There's a lot more to be dug out here. And supermassive black holes are not the only potential source of these kinds of gravitational waves, right? What we could be looking at are primordial gravitational waves from the Big Bang itself. And then cosmic inflation has stretched them out to be these colossal, hundreds of light years long wavelengths. Possible. inflation does that. It could be a sign of something called a topological defect, like a cosmic string or a domain wall. The basic idea behind a topological defect is that, like, think about water freezing. If you look at water freezing and crystallizing, you get some crystal growth over here, you get some crystal growth over here, and maybe they're aligned differently, and they grow together, and at some point there's a boundary between these two different alignments of the crystal. That boundary is exactly what a topological defect is, except here, the crystallization is the end of cosmic inflation. Ask a cosmologist. But the bottom line is, maybe that's a thing. There's no experimental evidence for it, but that would, those objects would in principle also generate very long wavelength gravitational waves. And then of course, we don't know what we don't know, right? I mean, what else could be out there? That's why we look up, right? Yes?
Is there any relation with Hawking radiation to this?
Hawking radiation is particle radiation that comes from the event horizon of a black hole. When you have particle pair production, that accidentally occurs too close to the event horizon, so you get a quantum fluctuation where, say, an electron and a positron get produced, and one of those guys gets unlucky and falls into the black hole, and the other guy doesn't. And when that happens, it is as though the black hole has radiated something. But that's not gravitational. No, that's more of a particle physics game. Yes?
Given that the Earth is rotating and it's traveling around the sun at the same time, and the sun is rotating within the Milky Way galaxy and rising and falling below the galactic plane, and then our galaxy is moving in the local group, et cetera, et cetera, et cetera. So, are there Doppler effects on gravitational waves, since both the observed objects and the observer are both moving in complex ways?
Well, in terms of pulsar timing arrays, no, because none of those, first of all, the point of observation in a pulsar timing array is actually the barycenter of the Earth-Sun system, not the Earth itself. So part of that motion is taken, they take into account that motion. But if you're talking about, you know, the absolute motion of the Earth through, you know, the world or through the universe, could you Doppler shift? Yeah, I mean, in principle, if you're moving toward a gravitational wave source, it should appear at a slightly higher frequency, and if you're moving away from it, it would appear at a lower frequency. How fast would you have to be moving away from a wave source for the frequency to Doppler shift all the way down into the nanohertz? I don't know. I guess conceivably, does this have anything to do with the expansion of space-time due to the acceleration of the universe? I don't know the answer to that either. It's an interesting question. Okay, so it is cool beans, right? Astronomy's taken another massive leap forward because, right, you think about it. Not even 100 years ago, astronomy was about visible light. And since the beginning, right, of human beings looking up, astronomy was about what we could see with our eyes. And then we learned how to exploit radio waves. And then we learned how to exploit all the other pieces of the electromagnetic spectrum. You have to get above the atmosphere to do it. But now, right, multi-messenger, we look at the entire electromagnetic spectrum of, you know, of what comes from the sky. But it's more than that now. Now we use neutrinos and other high-energy particles. We probe the insides of stars by looking at the neutrinos that come from the sun. And now we're beginning to observe the universe in gravitational waves. Right? Completely different physics. Astronomy is pretty cool, you know. All right, thank you. Questions?
So the way that things are going, the knowledge that we didn't have like a couple of 100 years or whatever. So what do you think that, it's a difficult question though, so in the future, should we have, how much money should we have and what kind of people we get together to know more about and become very comfortable about knowing the universe?
Well, I think, as always, these projects, I mean, look at to even do the most basic detection of gravitational waves, look how big LIGO had to be, right? That thing took 20 years to get built, and they built it, and they had to upgrade it for another 10 years before they became sensitive enough to measure anything. And now we need a bunch of those if we want to do actual proper astronomy, right? These pulsar timing arrays. Okay, those are cheaper because we already have the radio telescopes, but how long do we have to look at them? What will we learn from them? And no one has talked yet about, well, how would you actually make a gravitational wave telescope, right? That's hard. We're guessing, right? We don't, it's all about, people have great ideas. It's also about, you learn something about the universe and that prompts you to want to look at a different measurement, right? To look for something. I mean, the hard part is if I don't even know what to go looking for or what to look at, I don't know where to start. I need a hint, right? Something isn't right, or something that I don't understand. I think the question of what is going on cosmological scales are dark matter and dark energy really a thing, or is this reflecting some sort of problem with our understanding of what gravity is? Does general relativity need modification? Don't know the answer to that, but I think that's a very interesting question right now.
Who are the people you think will be ahead? The Chinese, American, the Russian?
This science is too big for it to be national. We're going to have to. I mean, look, the Chinese started doing a lot of things, and now their economy isn't in great shape. So who knows what they're going to be able to do. Ditto with the Russians. I think there are smart people everywhere, and this planet and the human race is too small for us to be worried about who figures out what the next biggest thing is. This is a group project, as they say.
Do you know if pulsars can spin up to relativistic speeds?
Let's see. If we have a pulsar that's 10 kilometers in diameter, and it's got I could do the calculation of what is the speed of a pulsar at its equator. It's probably fast. Is it 1% of the speed of light? I don't know. There got to be limits, right? At some point, even a neutron star will start to bulge. Who knows, right? I mean, look. The first thing you ever need to do is look at Saturn, right? And you're like, I think your camera's messed up. That looks squished. Nope, camera's fine. Is squished, right? Because it's spinning so fast. So, who knows? I'm certainly not an expert at the mechanical properties of neutron star, but I suspect if it was spinning that fast, it would likely throw itself apart. Yes?
What are the problems with space-based LIGOs? What's the biggest problem to solve?
You need a really big bucket of money. Right.
You don't need. You have vacuum, and
you have vacuum, right? You would have,
to,
if you in principle, right? If you have that thing sitting out at L2, it'll orbit L2, right? Like the Webb, like Hipparcos, or Gaia. There are lots of things that sit out at L2, and they really orbit L2. But the point is that they're nice and stationary out there. Downside, service calls are a problem. So whatever you put up there, the laser burned out. No. So I think the engineering would be an extraordinary feat to do something like that, especially given how complex something like LIGO is. I mean, that interferometer is an extraordinary piece of scientific instrumentation. And now if I have to do something like that out in space, where the reality is once I set it up, I don't ever get to go and service it, that's tough. I think there's a whole host of enormously challenging technical issues there, in addition to the big bucket of money. Yes?
You might have said it, but when you're measuring the gravitational waves, how do you know, like, in what direction the object is that caused it, or how far away it is, and all that?
For pulsar timing arrays, we don't. So that's what stochastic means. Just ripples. I mean, imagine like a swimming pool, except you have to have one without a boundary. But so where somebody has thrown lots of pebbles in, and it's generating all these ripples, and right at some point it just looks crazy, right? You can't see individual waves. You just see it looks all choppy. But that is exactly what we're talking about, right? With something like LIGO, right? If for instance, here, let's go back to this picture. Oh, I didn't put it in. Well, this will work. So if the gravitational wave goes through this way, it doesn't really stretch or compress this arm of the interferometer. So if and if it goes through this way, then it doesn't stretch this one. And if it goes through it some other direction, maybe it does both of them. And can the interference pattern tell you something about that? Maybe. But suppose I have another one of these, and it's somewhere else on the planet. That means that as this wave goes through, and my other array is over here, it trips this one first. So now if I have a handful of these things, and I know the timing, which again, not easy, but if I know the timing, and I can synchronize them all, then I can figure out which direction it came from. That's the basic idea behind the most primitive, right, telescope you can imagine. At least being able to say, oh, here they are, and it came from over there. What people are waiting for is, can you catch a supermassive black hole merger or a neutron star merger, and then when you see it, they may have done this already, but then can you get gamma ray and X-ray telescopes to look at that in that direction right quick and see if you can spot, because there's going to be electromagnetic energy that's released from that event as well. Can you spot all, can you do multi-messenger astronomy to spot that? And the answer is they haven't done it yet. They're certainly trying.
So just to understand a little more about, are you getting multiple wave fronts coming through? Like, is it just one pass through?
In the timing array,
you see multiple ripples, and then also we think of light as having distance. We think of visual magnitudes. Is that like when you talk about the interference pattern of motion on the size of a proton? Is that the equivalent of very low magnitude? Or very faint, faintness. So
the brightness of a gravitational wave. When we do that, talk about that one first. That has to do with how large are the distortions in space-time, and to see big compressions or stretches would require enormous amplitude, just in terms of the amount of energy that wave was carrying. And when you take into account the fact that a lot of times when they look, well, where was the source, right? They can look at the characteristics of what like LIGO measures and get a sense of, oh, well, that looks like it must have been, a 20 solar mass black hole merging with a 30, and it made a 40. And so where did all that mass go? It went into the gravitational waves. And so you have a sense of how much energy got dumped into that versus what you actually measured in terms of the actual stretch of your interferometer. And yeah, you get a sense of, oh, well, that energy drops off like 1 over r squared because it's a wave living in 3 spatial dimensions. And so, yeah, you get a sense of how far away it is. And some of these things are, billions of light years away. But they're so energetic that we can see them from across the universe. The first question was, remind me of the first question.
Oh, that's, when I remember hearing like an audio representation of one, and they sound like a real quick pass through, but is that sort of a repeating signal? Are you getting multiple?
Oh, no. So what you're hearing when they give you that audio representation is as these things in spiral over millions of years, possibly. At first, it's a very, very slow process. But when they get really close, in that last moment, they're speeding up, and they're going faster and faster and faster. And that's when you get that chirp, right, that you've probably heard. That is the very end of the process. That's the last, literally, few seconds of the process that's been going on for millions of years. Before that, they're further apart. The accelerations are smaller. The gravitational waves that they're emitting are not as high in amplitude because they're not, but as they get closer, those get bigger and they bleed off energy, and that's why you get this death spiral at the end where it all goes really quickly at the end.
And is this telling us something about the anticipated frequency of those events?
The frequency has entirely to do with how far apart are these two compact objects.
Well, I'm sorry. I don't want frequency in terms of the signal they're getting, but the how often those happen in the universe.
Oh, well, that's, at some level, that's just dumb luck. It's a big universe. So they're likely happening all the time, but our sensitivity to them is limited, especially with only sort of 2.5 observatories. Yes?
A couple of things. First of all, you were talking about multi-messenger astronomy, and I'm not aware of LIGO pointing to optical telescopes for black hole on black hole in spiraling collisions, but they have successfully done to neutron stars.
They have. Okay, that's the one that I was thinking of. Yeah, because I guess if two black holes merge, probably doesn't generate a bunch of EM radiation, but two neutron stars is going to be very bright, especially in and especially in X-rays and gamma rays and all that energy stuff. So yeah.
Yeah, and that was 6. And then a couple other comments too. One is I think it's fascinating that the work with the arrays has been done with what sounds like available instrumentation in the field, but it must take a large capacity, a lot of observation time to do these measurements. Are you aware of any programs to develop a specialized measurement array for doing this kind of work?
I mean, this is one of the big problems in astronomy, especially in radio astronomy, is just getting telescope time. The good news is you don't have to watch these pulsars continuously, because if you're looking for nano-hertz, right, where you're talking about a wave that that stretch and compression occurs over decades, and so it might be enough to look every once a week and check in on all these pulsars and see if anything is changing. Right.
That's the time.
Yeah. And then just the third thing, I hope before you leave tonight you'll get a chance to share the G-2 recent.
You want to talk about that? We can talk about that.
Yeah.
That's also interesting.
Go for it.
Go for it. So basically, what so for those of you who are not familiar, the muon G-2 experiment is measuring with incredible precision the magnetic dipole moment of the muon. It's just a little bar magnet, and like with any magnet, if you put it into a magnetic field and if the two things don't line up, it'll spin, it'll precess. And so what we're actually measuring is the precession frequency as we store these things and let them circle round and round. But the bottom line is that what we have measured is now more than 4 standard deviations away from the standard model prediction. And that's interesting because the standard model prediction represents our best knowledge of all the stuff that lives in the subatomic world. And why would you be that far off? Well, and as we refine the experiment, again, there was about a 3 sigma variation coming from Brookhaven. We verified that a couple of years ago. Now we've bumped it up to 4. By the time we include the last of our, the running of the experiment has just completed, we've got at least double the data in the can, and by the time we finish analyzing that, who knows how precise we'll be. I mean, we're already at, the resolution is already 0.4 parts per billion. So 0.4, 0.2. Yeah. Anyway, it's ridiculous is what it is. When I got into this game, I never thought we would measure that anything in particle physics would measure anything with that kind of precision. And boy, was I wrong. The bottom line is that there is this now tension between this thing, this measurement, and the prediction of the standard model. And something has to give. The measurement could be wrong. We could be doing something systematically wrong in our approach to making the measurement that nobody has picked up on, and so we could just be wrong. It's possible, but now much less likely that this could be a statistical fluctuation. I've been doing experimental particle physics for 30 years now, and I have seen 3 sigma fluctuations come and go. It happens. Get more data, and something that looked very promising goes poof. It's possible that there is a problem with the standard model calculation, that the calculation itself has a bunch of challenges, and the theory group could simply be doing it wrong. And there's a whole collaboration of very good theorists who are working on trying to improve that calculation. And the last option, which is by far the most interesting, is maybe the discrepancy is real, that we are getting the calculation right, that we are making the measurement right, and that would tell us that there's something we haven't accounted for in the calculation. There might be new particles, there might be new forces, we don't know. But this would be the first indication of truly new physics in quite some time in particle physics, because the standard model is annoyingly good. It went from, boy, we are so awesome, we have got a theory that predicts all these things, to, oh my God, can we please kill this thing so we can figure out what's next? But it won't die. And we have good reasons to think that it can't be the final answer. There are too many free parameters. It doesn't include any description of what dark matter or dark energy might be, assuming those are even real. Who knows? I've started to become more and more convinced that a tweak is necessary to our understanding of gravity, but something is probably happening there. What it means is going to require us to analyze the rest of our data, and also for the theory group to improve what they're doing and their confidence in their calculations. It's weird to think about a theoretical calculation having an uncertainty, but it does, right? There are limits to the precision of these things, especially this particular calculation. So, you asked.
So, which are the best 2 or 3 universities in the world that are using this subject?
The best universities? Oh my gosh, I couldn't tell you. There's smart people everywhere, right? I mean, they're just even at Podunk North Central College up the road, right? There's some pretty smart people there. Not me, but and it's a moving target. So again, science is not science is no longer this person or this place. This is an all of the above, right? So, yes.
I had the opportunity to go through the Livingston LIGO facility at the last upgrade that they made before they made their discoveries. And the people there were pretty down because they had been observing now for quite a while. They would upgrade, they'd observe more, they'd upgrade, observe more, and they were telling me we were going to run out of funding. If we don't find something soon, we're in big trouble. And so they kept the faith, they upgraded one more time, and bingo. So maybe you can take some inspiration from that.
You never know, right? I mean, that's why you actually perform the experiment, because in the end, you don't know what the universe is going to tell you. So you have to look, you have to ask. But yeah, the money game, it can be frustrating. This country just doesn't spend the money on basic research that it used to. And, it's hard to justify. How's knowing about gravitational waves going to make our lives better? where you know, will it improve my toaster? But also, we do it for the same reason that, you know, that we write songs and create paintings. It's because it's what it means to be human. What did Carl Sagan say? The reason, you know, humanity and the science that we do, it's a way of the universe coming to know itself. So that's why.